Hello, Jack Jackson here. In this video, we're going to use a GeoGebra activity that I created to look at different ways of approximating the definite integral. So I have this applet here. It allows you to change the function by typing in the formula right here. You can move this around with your mouse, zoom in and out with the scroll bar. And you can set the interval that you're integrating over with these sliders. So I can slide this around or just type in a number here. So for example, if I want to go from, this works out pretty nicely if I just go from 2 to 6. So let me do that. We'll go here at 2. And we'll go to 6 here. And this lets us control the number of subintervals that we're looking at. So let's just start with 2. Now what we're trying to do is we're trying to look at this area right here and approximate this area. This area is actually what the definite integral is going to give us, the integral from 2 to 6 of this particular function. And we want to approximate that with some shapes that we know and understand. So the first way we can do that is with what's called a left Riemann sum. And so we're going to break it into n subintervals. So we take this interval from 2 to 6 on the x-axis, break it into whatever n is on the subintervals, in this case 2. And we're going to break it into rectangles. And so the rectangles have to have some height. Their base here is delta x, which is in this case 2.
Just a sec.
And what we want to do there is get the height of these to be at the left side of each interval. Now, by the way, the widths are going to be the same the way we're doing it. And notice that the length of that interval is from, well, in this case, from 2 to 6. Which is the length of 4, which we found by doing 6 minus 2. If this is A on the left and B on the right, then that interval is going to have a length of B minus A. And if we divide it into n equals lengths, each one of those will have width delta x, which is B minus A over n. Notice that's displayed up here in the little box on the information box here on the left. So, and notice as we increase that, we can change the value of n. But every time we're going at the left side. Now think about it a minute. If it's a left Riemann sum, it would be perfect if this was horizontal. And if the function is increasing, the left Riemann sum is going to be underestimating on this portion. But when the function is decreasing, the left Riemann sum is going to be overestimating our interval. Now compare that to a right Riemann sum, which is basically the same thing with just a slight variation. Instead of going to the left-hand side of each interval and coming up and finding the height, let's put them both on there. So instead of coming here to the left side, we go to the right side for that interval. And so that's a right Riemann sum. And we get that set up like that. Now notice the right Riemann sum is sort of backwards from the left Riemann sum in the sense that if the function is increasing, it's an overestimate, and when the function is decreasing, it's an underestimate. So notice that that's actually good news, because this tells us if the right Riemann sum is too big and the left is too small on a particular interval, then averaging the two should give us something better. And so if we just make sure that it's all increasing or all decreasing on each subinterval, then certainly averaging the two should give us something better. So averaging these two is something called the Trapezoid rule, and that gives us rectangles that are halfway in between the left and the right Riemann sums here. In fact, let me go ahead and show you the definitions of these things. So here's the left Riemann sum and the right Riemann sum. Let's back up just a little bit. So here's the right Riemann sum, and here's the formula for it right here. We're summing n areas of n rectangles. So the sum is going to go from k equals 1 to n. All of them have the same delta x, which is given by this formula, b minus a over n. And then to get to the right side of each subinterval, we take a plus k delta x's. So a plus 1 delta x will get you the right end of the first rectangle, and then you do f of that to get the height. Multiply by the width of delta x, and this gives you a area of one rectangle. Add that up for all rectangles. You get the total of all those red areas. Okay. To get at the second interval, at the right side, we do a plus 1, 2 delta x's. So in general, to get the right side of the kth interval, you go to a plus k delta x. Then once you're there, you find f of that to find the height here, and multiply that by delta x to get an area, and then sum those up. Similarly, for the left Riemann sum, it's the same thing. Sum from k equals 1 to n is delta x times an f value. But this time we want to be at the left side, so to do that, we do k minus 1 delta x's. So if k is 1, that's 0 delta x's plus a, starts you at the left side. If k is 2, that's 2 minus 1 is 1 delta x plus a, puts you at the left side of the second interval, and so forth. Okay, if we average the left and right, L plus R divided by 2, this gets us this trapezoid rule estimate. So let's take a look at that again. So there are the heights of the left and right rectangles, or the whole left and right rectangles. So what we want is we want a rectangle that splits this halfway between these two heights each time. And that's what the trapezoid rule estimate does. If you look, these purple rectangles are exactly halfway between the left and right rectangles in their heights, and thus exactly halfway in between in their areas. So if we just average those on each one, we're going to get those rectangles there. And so this gives you a way to illustrate the trapezoid rule, it's called, as rectangles. But now wait a minute, why would I call it a trapezoid rule? These are rectangles. And certainly we want to think of then rectangles as being the average of the right and left rectangles. But what I also want to show you is you can also think of them a different way. Let me pull this down to a smaller one here. So if we look, say, on this rectangle right here, this one in the middle, I'm going to claim that this right trapezoid, which is got the same base and more or less the same sides here, but it goes up to points on the graph which are at the left and right ends of the intervals to make a secant line segment for the top. I'm going to claim that that's the same area as the area of this rectangle right here. And let's see, what do we know? Well, we know that because, remember left and right, this guy is exactly halfway between the left and right here, then we know that this distance right here, if you can see it, from the height up to the curve here is the same as from the height here down to the curve here. So we know those two are congruent. We know it's a right angle, those are congruent. And we know vertical angles are congruent, these two right here. So by the side theorem from geometry, you know those two triangles are congruent, and therefore they are the true shapes are congruent. So basically what I'm saying is you can cut off this little triangle right here, rotate it up and land it up here, and it makes a nice trapezoid. So this is why this is called the trapezoid rule. We can think of it as rectangles, but it's the same area if we think of it as these trapezoids. So the trapezoid rule is essentially approximating with a linear function, whereas, say, a left Riemann sum is essentially approximating the function with a constant function on each one, as is the right Riemann sum. But the trapezoid rule is approximating with a linear function on each subinterval, with those intervals, with those linear functions being secant lines, or portions of secant lines. So we have secant line segments for the top of our trapezoids. But the easiest way to find it is just to do the left and right Riemann sums and then average them. So the trapezoid rule is going to give us a little better estimate. Here are the actual values, for example. On this one, the actual estimate the actual area there to, well, it's 19 1/6 exactly, but to this many decimal places it's 19.16667. It's actually 0.16, the sixes repeat exactly. And we can see these different estimates. There's the left, the right, and the trapezoid. And I'll get to these other two in a minute. Okay, and so we can see that as well. But the left and right estimates are not as good in general as the trapezoid estimate. Okay, so let's look at a different way of looking at it. So another way we can look at it with, instead of going to the left or the right side, we could go to the midpoint. Now this time, this is not necessarily the same distance, like you can really see it on this last one here. This one here is much closer to the left, on the top, as it is to the one on the bottom, the right. So those are not the same distance here and here, these two little pieces. But what is the same is the horizontal distance, the distance from here, the left side of this top of the rectangle to the curve, and then from that curve to the right side. So this point right here is above the midpoint on this interval down here. So this is what's always called the midpoint rule estimate, and this gives us rectangles like that. They go up to the midpoint. Now at first glance you'll say, well, that's pretty much like the left or right. We just chose the midpoint instead of one end or the other. But in fact, it's actually a lot better than the left or right. It's actually a lot more like the trapezoid rule, because the midpoint rule can also be viewed as a trapezoid instead of a rectangle on each piece. Okay? This time the trapezoid that we're looking at touches at this point where the graph touches the rectangle for the midpoint. That again, x value, that's above the midpoint of that interval. Look, what's happening here is we sort of take this and make a tangent line segment where it's tangent to this point and the midpoint of the interval. So I'm just looking at this one on the right here, for example. And I claim that this trapezoid has the same area as this rectangle. And you can see that this way. Now, this is no longer necessarily same distance from the top and bottom of that thing like we had before, right? But what we do know, it's the same distance horizontally. So we know the distance from this point here, the right angle, to the curve is the same as from the curve to this point, the right angle there. And of course we do know we still have two right angles, and we do have still vertical angles here. So this time it's the angle side angle that allows us theorem that allows us to say these two triangles are congruent, which again allows us to cut this little piece off of the rectangle, rotate it up, and place it up here to make a trapezoid. So in fact, the midpoint rule is really probably it's most easily thought of as rectangles, right? You just find the midpoint and find the rectangles. But in a way, it's more properly thought of as a trapezoid type of estimate, right? Estimating with trapezoids. Okay, so both the trapezoidal rule and the midpoint rule are estimating the function with linear functions, or estimating these areas by making right trapezoids. Now, the actual definition of the midpoint rule is more easily said in terms of the rectangles that you see here. And of course, here's the formula of it right here. We go to the widths are still delta x like before. We're still going to sum up n rectangles from k equals 1 to n. So for the first rectangle, you want to go to the midpoint here. So you want to go k plus a delta x, but then you want to back up a half a delta x. So k minus a half delta x. So 1 minus 1/2 is 1/2. It's a half a delta x we add to a. So we add a half a delta x here. Oh, find the height there. Multiply by the width. You've got an area of that 1. So for the second one, notice what we do. We put in a 2 here. 2 minus a half. We go 1 1/2 delta x's. puts us at the middle of the second interval, and so forth. So this formula right here, this a plus k minus 1/2 in parentheses delta x, that puts us at the midpoint of each interval, horizontally midpoint, right? And then do the f of that gives us the height above that, and then multiply that by delta x gives us an area of that rectangle, and then sum those up gives us that midpoint estimate. Notice that's all really defined in terms of thinking of it as rectangles, but we've also seen that we can equivalently think of it in terms of trapezoids. Now, so which one's better? Trapezoid rule or midpoint rule, and when are they over and when are they under? Well, if you look, if the function's concave down, like here, the trapezoid rule is going to be an underestimate, whether it's increasing or decreasing, whereas the midpoint rule is going to be an overestimate. Now, if we're looking at, let's say we're looking at a portion over here, where it's concave down, notice it's exactly backwards from that. Say right in here, oops, let's just go to 0. Concave up piece. Yeah, that's fine. A concave up piece like here, that it's the trapezoid rule is under, and the midpoint is below. So they're actually backwards from each other. In both settings. So that's good news. So let me just go back to the original one I was looking at. Let's say from 2 to 8 again. Now let's go to 2 to 6. So again, the both the trapezoid rule and the midpoint rule are essentially approximating the function with a line segment. The tangent line segment is what we're using at the midpoint, is what we're using for the midpoint rule. And the secant line segment at both ends of the interval is what we're using for the trapezoid rule. So if the function were linear on each of these pieces, both the trapezoid rule and the midpoint rule would be the same, and they would be perfectly estimate the integral on that interval. So what if it's not linear? Then it could possibly be all concave up or all concave down on a small enough piece. And so what could happen here? Okay, well, take a look at this. Since one's over when the other one's under, that gives us, we should get a better estimate by averaging those two. But the thing to notice here is one of these is better than the other. Can you tell which one it is? Look at this last piece here. The trapezoid rule is, here's the area we're looking for, right? So the trapezoid rule is under by this piece right in here. Whereas the midpoint rule is over by this amount and plus this amount here. Well, which one of those is actually better at coming at that? Well, if you look, this area that we're under on the trapezoid is actually quite a bit bigger than the area that we're over on the midpoint estimates. In fact, it's roughly twice as big. In fact, if this was a parabola, it would be exactly twice as big. So for that matter, we would say that, roughly speaking, the midpoint is going to be about twice as good as the trapezoid. So it's better than just adding them up and dividing by 2 to get the better average. Let's count the midpoint more in the approximation when we average. So we're going to take the trapezoid rule plus 2 midpoints and divide by 3, and that's going to give us an estimate that we call Simpson's rule. Now notice Simpson's rule is, the way I think of this, is still 3 intervals, but we're taking information from both the left and right to get the trapezoid estimate and from the midpoint to get the midpoint estimate, and then we're working that together. Some folks, however, would think of this as being actually each one of my intervals being 2 different intervals, with how you handle both ends differently. So typically the normal way this is done, Simpson's rule, this would be Simpson's of twice n. So right now we have left 3, so let's just go back. Left 3 is the estimate here, and that's 13.3 repeated. We have right 3, which is 3 rectangles. That's about 20.09 in area. We have trapezoid 3, which is either those rectangles or those trapezoids, for an area of 16.7. We have midpoint 3, which is those rectangles or those trapezoids, for an area of about 19.5. And if we average those, we're going to get Simpson's, but Simpson's is Simpson's 6, not Simpson's 3. So for Simpson's 6, we take the trapezoid, 16.71, whatever, plus 2 times this midpoint, get that first, and divide by 3, and that gives us the Simpson's estimate of 18.59. Now, it turns out that Simpson's rule, another way to get it is to approximate these things with parabolas. So probably the easiest way to do that is just to see it with one interval. So we take the middle of the interval, and the parabola is going to hit that point. This end here it's going to hit, and that end's going to hit here. And so we had a parabola that hits through those 3 points. Remember, for a constant function, you just need 1 point to define it. For a linear function, we need 2 points that it goes through. And to identify a particular parabolic function or quadratic function, we need 3 points. And of course, the 3 points are the 2 endpoints of the interval where it crosses where it's above the part of the graph above those 2 endpoints of the interval, and the part of the graph above the midpoint is the 3rd point there. And of course, we can take that and increase it. Let's say put 2, and you can see that. And you notice that we're already getting very close to this. So Simpson's rule actually works really well. It doesn't take a very big of an n to get Simpson's rule to be quite close to the actual curve on the top, and the area to be quite close there. Now, of course, the bottom line is no matter which one of these things we're looking at, whether it's left Riemann sums, as it goes closer here, as n gets bigger, it gets closer and closer to the integral. Right Riemann sums also gets closer to the integral as we let n be there. We get closer to that exact value when we let the trapezoid rule, whether we're thinking of it as rectangles or trapezoids. The bigger n gets, the closer that's going to get to being the area. And midpoint does even better still. Trapezoid's better than left or right. Midpoint's better than trapezoids. So you think of that as either rectangles, or we can think of that as trapezoids. But either way, we're getting closer and closer. But Simpson's rule works even better. And Simpson's rule is the area there. I don't have it shaded here, but it's the area there, and it gets closer and closer again as we let n get bigger and bigger. You can look at the numbers down here and see them converging as well. And of course, the thing that it's coming in on here is the definite integral, which is that. We could take the limit of any of these, and it would approach that definite integral. But so basically, I took the simplest one to define it from the right Riemann sum. Took that limit take that right Riemann sum and took the limit as n goes to infinity to get that integral. But in fact, they all converge to that, and Simpson's rule, of course, is going to converge the fastest. It doesn't take a very big n for this to work. And so Simpson's rule turns out to be a very, very powerful way to numerically approximate this integral. No matter what it is, all you really need to do is be able to evaluate the function at different points And the rest is just some basic arithmetic. Now there's a lot of it if n gets big, but this is how we approximate this integral with various different methods, and you can see that this particular GeoGebra applet lets us experiment and demonstrate and play around with this for different values. I do want to mention one more thing before I get off of here. I've been talking about areas the whole time, but in fact you have to be a little careful, because let's say if we go from -2, when we let's see, here. Now look what happens, say, on this piece right here in the middle, when we do, say, just do a right Riemann sum. The y values are actually negative numbers. Okay, the way we've got it set up with a being less than b minus a over n is a positive number always, because we're going a is less than b. But the heights are negative. Now the height is always positive, but a signed height, the f value, which is what's actually here, not actually a height, but a signed height, that value could be negative. So these right Riemann sums could be actually a negative number. Say if we just went from, say, from negative to, let's see, -1 to 1, for example. And whether we're doing a right Riemann sum or whether we're actually doing the integral, you don't actually get this area, you get the opposite of that area. You get a negative number. And so you have to be a little careful of that. So for example, if we go from -1 to 7, for example, then what you're going to end up with for the integral is actually this area here above the x-axis minus this area below. So what the integral actually gives you is a net signed area. Okay, a signed area could be positive or negative, and it's a net signed area because it's the total area above the axis over the interval between the curve and the x-axis that's above minus that area that's below the x-axis. So if there's more area above, like there is here, then you're going to end up with a positive number. If there's more area above than below. If there's more area below, it will be negative. So if I take this b and bring this down here, okay, so right in here, we're still more above than below. At some point in here, I don't know how closely I can get it to work out, but somewhere in here, the balance, somewhere in between there and there, this and this balance out, and the integral is 0. But if there's somewhere in here, for example, there's less area above than below, so you get a negative integral. All right, so I think that covers everything I wanted to do here. Kind of a long video, but I hope it explains a lot about approximating the integral. Went over the definition of the integral as well, and it went over the tools that we have in this particular GeoGebra activity. You can get this from GeoGebra site very easily, or in my my calculus collection of things from GeoGebra that you can look at as well. So hope you enjoyed this. Hope you can find that useful and maybe find this applet useful as well. Bye-bye.